All right, so this little exposition, it's about binary diffing. So how to get differences from between different instances of binary data in contrast with text data. So first, I will go through some existing programs and existing approaches for doing this, from the more simple to more complicated to more sophisticated. Then I will create, I will expose, a proposal for a new format for a structured binary data with an emphasis on the structure. And then we can discuss about this format because there are a couple of open questions about it. And this is something that would be nice to actually design, to agree and to have reach some consensus, because this can be implemented by other tools. And then I will show a little bit how the implementation in POC of this format is implemented, because I think it's nice. All right, so let's start. When it comes to compare binary data, the simplest alternative I have found is the CMP command, the CMP Unix command. It has an option. I mean, by default, when you run CMP into files, you get just whether they are the same or the offset of the first byte where the two files differ. But if you pass the option -L or -- verbose, then you get basically the relation of all the bytes that are different between the two files. So in this case, here, if we run CMP -L foo.o and bar.o, here is basically telling us that at offset 41, the byte at the offset 41 goes from having value 10 to having value 350. The byte at offset 42 changed from having a value of 2, and now it has a value, and it has in the second file the value 4, and so on. Well, then of course you get an entry for every byte that has. Yeah, I don't know. Yeah, I know. I don't know why this is 350. Anyway, whatever. It's the new value, or it's supposed to be. Maybe it's a copy paste error that they made. Yeah, probably. Anyway, this kind of information that you get from CMP, it is so readable that actually we are wondering what's the meaning of this number, right? So, how useful is this information that we get from the command? Well, I guess it is good to be used programmatically because it is easy to parse the columns and to get the numbers and to interpret them and operate with them. But when it comes to readability, it is basically null, because for a person, I mean, by just looking at those numbers, at those bytes that change, all we know is that some bytes change their value, but nothing else. And also, this gives us all the differences in the file. So you basically can't tell CMP that you are only interested in some portion of the file, because to begin with, how do you determine what portion of the file you are interested in? Anyway, this is useful. Yes, this is one possibility. Another possibility is to use some combination. So to get a textual representation of the binary contents of the file, In this case, I am using XXD, but you could use object copy to get an S record representation, you know, something like that. And then the diff command, the normal diff command. So in this case, this is an excerpt of the output of diff minus u, you know, of the output of XST from foo.do and bar.do. And then we get a normal unidiff with the differences. Note that I have not included the full output here because there is a long, you know, there are so many differences between those that this is actually a big block of differences. But well, we could open this diff into a text editor or even into one of those graphical utilities that makes it easy to see, you know, to visualize diffs and then see the differences. Yeah, well, this sort of works. It is not good to be used programmatically because obviously you will need to parse everything here. I think that Matthias showed that in FQ he's doing something like this to import data from other programs, like trimming the spaces and removing those columns and everything. But, well, on one side, this is not good to be used programmatically. On the other side, this is not that easy to read by a person because as I say, this block is big. So there is not much locality, right? I mean, and also because at the end of the day, all you are saying here are raw bytes, right? And well, the ASCII dump that sometimes is helpful, sometimes it doesn't, it is not. And also you get all differences. Again, you can't determine, you know, a subset. You can't say, I'm only interested in this area of the files. No, you get everything. Then there are some tools which are more sophisticated, like radiff2, which is part of Radare2, which is a quite nice suite for reverse engineering and also binary tampering. Well, there is a command called radiff2 that it gives you the difference. Okay, let me see if I can interpret this properly. From the offset in the file, it gives you also the changes, like those 2 bytes turns into those 2 bytes, those 1, 2, 3, 4, 5, 6 bytes turn into those 6 bytes, and so on. Then you can pass an option -r, and then if you pass the option -r, radiff2 generates commands for Radare2 that you can actually just inject into the command line application, and then it will basically change foo.do into bar.do, right? Which is, this is useful to generate some sort of patches. Again, well, Radare2 is good, is mainly used for reverse engineering. So it knows about symbols, it knows about object files, and it is actually very good for disassembling and so on. So the radiff2 utility, it has options in which you can tell it that I only want to see the differences in this function. So you are telling radiff2 that this is an L file and I'm only interested in changes on this particular function or for this particular symbol, which is better than getting everything, but it is obviously tailored to the main purpose of the tool. In this case, Radare. Then there are other utilities out there, which they are all very similar. So I got the dhex, the diff mode, but there is a vbin diff and many others, which one way or another, they get like a dump of bytes, and then they put them either, well, side to side or top down, like in this case. So you can, and then as you can see, it highlights the bytes which are different, and the parts in the ASCII dump which are different. Well, yeah, this is nice too. You can have a visual, some sort of visual representation of the differences. How useful this really is, well, I don't know. I mean, I'm not saying it's not useful, but at the end of the day, I mean, what is this? Those bytes? What are those bytes there? Well, who knows? I mean, if you really, I mean, this is useful to you if you know where to look and you know what you are looking at. But obviously, that is not. I mean, that's not obvious from the tool itself. So I consider the hex diff mode and Vivin diff and the other tools basically a more user-friendly or more sort of visual version of the previous approaches that we have seen, but not actually very different to it. So considering this, the question is now, how useful are those differences? Obviously, they are useful because otherwise those tools will not exist. But consider, for example, the following scenario. Imagine that I am working on the linker, and there is a bug which I know it is related to handling of relocations in the object files. So imagine that I have an object file that reproduces the problem, and I have another object file which is very similar, in which the problem does not happen. And of course, I don't know what the problem is yet because I am debugging the linker. But I know that it is related to relocations. So what I will need to do, I will want to do, is to get the difference between those two object files, specifically in the part where the relocation information is stored in the L files, right? And I don't care about anything else, right? I mean, at least at this point, at this stage, I don't care if there are other differences in the L file, differences in the string tables or differences in other fields. I want to focus on that particular area. And also, I am interested not only in the difference in the row bytes, but where exactly in the relocation information, what are the consequences of those differences in the bytes, right? So that's what I would like to have. And if I had a way to express those differences in that expressive way and localized way, I could actually not only apply it automatically to reproduce the bug and debug it, but I could actually use it to document what the problem is, or to put it in a Baxilla, and so on. So for this purpose, I propose the following format for this kind of diffs. For lack of better name, I call it a structured binary diff format, or SBDiff, but this name I know it is not very good, but anyway. So basically, in this format, you have a sequence of thanks similar to the ones in Unidiff, in which each thank, it has a header. I use the same format here than Unidiff, you know, this add. And you have basically A information and B information in the header. So from information and to information. So the A offset is basically the base. So the offset of the A, in this context, A is the minus and B is the plus. You will see it in the examples. From the beginning of the file, of the A file. And AS is the size of A, also in bytes, which is the size in the origin to which this thank applies. Then you have an offset in B, and the same thing, the size in B. This is optional and this is optional. We will see now that depending, some tags only contains addition lines, some tags contains only removing lines, deletion lines, and some tags contain both addition and deletion lines. So then in each tag, you can have 0 or more, well, yeah, 0, actually, yeah, it could be 0 or more lines, which could be either addition lines or deletion lines, depending with a plus or with a minus. Then you have a textual representation of the bytes, in which you can have blank spaces to group them by, we will see now. Then you can have an optional symbolic name that applies to the bytes preceding it. And then you can have an optional string denoting somehow the value or the semantics of those bytes here. We will see, let's see some examples. You will see very fast how this works. Anyway, in POC, there is I added a new command which is called diff, which is in the branch, in the master branch. Is not in POC 2.1, so you have to use the Git version if you want to play with it. Then the synopsis is very easy. You have to pass an A argument and a B argument, which must be mapped values. And then you have an optional argument values to show, actually to include this part in the diff. And then you can specify how you want to group the bytes in each line. Okay. So let's see a first example here of structured binary diffs. This is the definition in the ELF pickle of an ELF header. So basically, here I am getting the difference between the header of one given ELF file and another one. And basically, I'm getting two tags. As you can see in the first tag, well, basically, you see how useful the names and actually also the values here, right? So this is basically telling me that the second ELF file, the section, the section header table is in a different position in the file, right? So in the first file, it is 520 bytes from the beginning of the file. In the second one is 1,256 bytes from the beginning of the file. And also, the first ELF file, it has 11 sections. The second file has 19 sections. And also, the first file has 10 entries in... No, sorry. In the first ELF file, the meaning of this field is basically that the 11th section is the section that contains the string table in the first ELF file, and it is the 17th section in the second file. So you can see here that just by looking at the output, you know exactly what is different between those two files, and only in terms of ELF contents. So, because of course ELF1.ehtr and ELF2.ehtr, they are POC values of this struct. So any other difference, in the file that is not covered by those mapped values, you don't see the differences. Also, you could actually get the difference between the full ELF. I will show you later. But this is one example. Of course, if you look at the header here, this means, so this is the A part, so the front part, which means that in this minus line here, this means that those bytes start at offset 28 hexadecimal from the beginning of the file and span for 8 bytes. Okay, in this case, you can see it easily, right? So 1, 2, 3, 4, 5. And so this is basically telling you that 8 bytes are added in this tag from this offset. are removed from the A file in the difference, and 8 bytes are added, starting at that offset in the B file, in the output file, right? The second file. And something similar here. In this particular example, the sizes are the same. You removed 8 bytes, added 8 bytes, removed 4 bytes, added 4 bytes. So let's see an example where we have thunks that only remove data. Consider this POC type here. You have the typical struct that we always use for examples, where you have 1 byte, which is the size, 1 byte called B, that is just in the middle. I'm using it so those thunks don't get mixed, because the implementation is sort of smart and it combines thunks, so you don't have many thunks, but because it is more readable. And then you have an array of bytes here with the data. Now, of size here. So if you see in the current IO space, it's all 0, but the first byte here is 4. So I'm asking POC to give me the difference between a foo, a struct like this mapped, an offset 1, so mapped here, in which size will be 4, and another foo mapped at offset 2 bytes. So it will be mapped here with everything 0. So the size of this array will be 0. And we see the difference here in the diff. So this is telling us that the size switches from 4 to 0, which is this field here. B is the same, is 0 in both cases, so we don't get any difference for it. And then data, it basically gets removed. Those 4 elements of data of this array disappear, right? From the A value to the B value. So that's why we are getting a thunk here in which we only have coordinates for what is being removed, but this is not being substituted by anything. So that's why we get a thunk with 4 deletion lines. Note that if the value is a byte, like in this array, for example, elements, we don't get a value here because it will be very redundant, right? I mean, the value of a byte is just this. So conversely, we have the same struct type here. We have the same contents in the IO space, but now we are comparing the foo mapped at offset 2, so everything zeros, with the foo mapped at offset 1 byte, which the array with 4 elements. So we get now the size switches from 0 to 4, and we get a thunk with only addition lines, and that's the reason why now the coordinates are after the comma here, right? Okay, so what happens if we remove this field B here, right? If we remove the field in the middle between those, POC basically combines the lines into a single thunk, because you don't need more than one, because this covers a continuous space in the changing space, so to say. But this thunk that we get, it has 1 deletion line, 1 addition line, sorry, 1 deletion line, and 1, 2, 3, 4, 5 addition lines. So it's very readable, I think, because this is telling you that the size is changing from 0 to 4, and then here you get the addition of the 4 elements of the array, right? In this case, obviously, we are deleting one byte here, starting at offset 2, and we are adding 5 bytes, starting at offset 1. Yes. So this is an example of how the thunks are try to, and combine as much as possible. Okay, the sdiff command in poke, it supports an argument group by. By default, as you have seen, okay, this is a bad example because those are all bytes here. As you can see, by default, it uses a grouping of 1 byte, actually. So it shows you the digits, the representation, the hexadecimal representation of 1 byte each. But very similar to the dump command in poke, you can group in a different way. Like, for example, group by 2 bytes. Well, you get this. You could actually group everything together.
Jose?
Yes?
I guess a question here. She's
Okay.
coming to my microphone.
Oh,
Yes.
okay. So basically, when we had the byte in the middle in the previous examples, yes, for example here.
Yes?
No, in the previous one, I think, yes, what is the difference between removals and additions there?
Okay, here we are going from a full mapped at offset 1 byte. So here,
Okay.
in which size is 4.
Yes.
In comparing it with a full mapped at offset 2 bytes, which is here, in which size is 0.
Exactly. Can I see the next slide?
The what, sorry?
Next slide.
Oh, yeah.
Okay, this is from 2 to 1.
This is
That
from
is
2 to
why
1.
removals became additions. Okay, that was my question.
Because now we are comparing a
Yes,
full
from
with an
2 to
empty
1.
array, because it starts at 2, so the size is 0, with a full with an array with 4 bytes.
Yes, I didn't notice that you switched them.
Yeah. I know. It's a little bit confusing maybe, but it was a fast way, to show the switch here, right?
Yeah.
Yes. Yes, this is from 2
Okay.
to 1, so from 0 to 1, and this is from 1 to 2. Yes.
Okay, thank you.
Thank you.
Okay, so this was the combined thanks. The grouping bytes. This is an example. You can actually ask the poke implementation, the sdiff command, to not include values. I have not implemented an option to not include names because I don't know. I failed to see why would that be useful in the poke context. But know that the format itself should work programmatically with names or without them, right? I mean, because it's only this part that it's actually relevant programmatically. But it is this part that makes it more interesting for us. Of course, how does this work with some of the interesting poke features, like, for example, absent fields here? So we have the same IO space, and now we have a struct foo, in which it starts with a byte, and then it has an integer bar field, but only if the previous byte is not 0. So again, we are comparing a foo mapped at offset 0, in which foo is 0, so it has no bar, and a foo mapped at offset 1, in which foo is 4, so it has an integer bar. So we get one thank with yes, we have a thank which the byte, the first foo, so foo changes from 0 to 4, and then since it changes from 0 to 4, then there is also a bar, which in this case it has 4, and the value is 0. And if I do it the other way around, so it goes, foo goes from 4 to 0, and then I don't have a bar anymore, and that is denoted with the removal here. Unions also work as expected with this. So let's suppose we have a variable x. We have a union that can be either a byte foo or an integer bar, but only if x is not 0. So first we have the same IO space. So 0 and 1. Okay, since x is 0, this mapped foo and that mapped foo okay, changes. Yes, exactly. Since x is 0, those two foos, they have a byte. So the alternative that is foo, the one that is active. So it tells you the difference. But if we change x to 1, and then we map those values again, then it shows you the difference of the int, which is the alternative that it's in effect. So yeah. And this is an example with comparing the string table of an L file. And here you can see how. Okay, this I would like to show actually. I would like to show in a different. So I am opening 2 L files. Those are 2 L files. Load elf. I'm loading a file foo.pk that I have in my directory that actually gives me the elf1 variable, elf2. It does some mappings for me. So this is the string table of the first L file. This is the string table of the second one. So you can see here that, well, you can see the difference, right? I mean, you can see that the entry, the 7th, well, actually the 8th entry in the first string table, it changes from .comment to .rel at the back info. And yes, the difference between those 2 L files is that the second one has the backend information compiled in. So that's why it has a rel at the back info section and the other one doesn't. Note how the node GNU stack, it goes to a different entry. And note how basically the entry 7th changes, the entry 8th changes, the entry 9 changes, and there are some new entries here in the string table. Which, by the way, we knew because we knew this, right? Okay, let me switch. Yeah. So we knew this. That, okay, no, into the table. Well, yeah, that it was a difference between the number. Yeah, here it is, of the sections. So it makes sense that in the string table with the name that contains the section names, there is a difference too. So this will be comparing from the first L file to the second, but we can, of course, reverse it. And then we get the same difference, but the other way around. So, and I think that it is very much readable. Now, what is the good thing about this? This is, of course, not specific to ELF. I mean, this works for every POC struct that is defined the proper way. And so, for example, we can say compare the ELF files entirely. So ELF1 here is basically all the ELF1, the data from the first ELF, and the ELF2 is from the second. So we can say sdiff ELF1, ELF2, And then we shall see, well, we see here the header differences. Here we can see this is clearly, you know, SHDR. So this is the fifth entry in the section header table. There are those differences. We can see, I don't know, those flags for the section flags are changing from 2 to 0. In this case, there are changes in those sections because those section entries are used for different kind of sections. And then at some point, as you can see here, at some point, those are the new entries in the section header table. Yeah. And it works for every epoch value, mapped value. So if we change the pickle and we want to compare CTF data, it will work. BTF data, it will work. Be whatever. So this is the format that I propose basically to adopt for this kind of diffs. Now, there are some open questions that actually I'm interested in your input. As you can see, you have seen the proposed format is byte-oriented. It's totally byte-oriented. In the header, we have the offset denoted as bytes, the size denoted as bytes, and even in the bytes, we could go down to nibbles, but it uses hexadecimal digits. So my question is this good enough, or we should change it? Because I see three alternatives, as you can see in the slide, or at least three alternatives. We could support bytes and nibbles. I'm saying nibbles because of using hexadecimal, you know, in the byte lines. The second alternative is to support bytes and bits. Of course, if we do this, we will need some special sort of notations for the offsets to denote, or even for the patch. Maybe the patch or the thunk could have some sort of flag there that this is bytes or bits. But then if it is bits, obviously the digits in the bytes line, it will not be a bytes line anymore. It will be a bits line, right? It should be interpreted in a different way, but that could work. The third alternative is to support arbitrary units. This would be very easy for us from the POC perspective, because we support arbitrary units, and for us it's just a matter of writing offsets there, right? And any offset is good for us. But they realized that could be overkill for other tools, and also it will make the patches, well, not more difficult to read, but you know, not as straightforward to parse and to interpret. And I really think that this format should be simple enough to accommodate more tools. So, what do you think? Any opinion? Okay, I guess not. Okay, then I will do whatever I want and fine. The second question is context support. At the moment, there is no context because, I mean, for a format like Unidiff or textual diffs, the context is something that is obvious, right? I mean, the context are the lines above the change, and below the change, because all the diff, most of the diffs of the diff context utilities for text are line-oriented, because text is naturally line-oriented somehow. But in case of binary diffs, I mean, we don't have the notions of lines. Do we have any similar notion and a similar concept there? I'm not sure. I don't think so. I mean, yeah, we could have contexts like byte contexts, but I'm not that sure that will be useful. Yeah. Array members. Yeah, okay, but then the context will be based on a structure, not based on bytes.
The context would be based on an array, not a struct, strictly an array.
Yeah, but the problem here is that
It is elements.
Yes, but the consumer of the patch does not know about about the struct.
Yeah.
I mean, the name of the fields and the values is for human consumption, so to say, right? It is the bytes parts that are consumed, unless we add something in the header of the patch and then we say this patch has been generated by this particular type in poke, right? We could hash the type, for example. So then if it is poke the one consuming the patch, it could be smart, because it knows what comes first and what comes after. But for other utilities, that will not be useful. So I think that it will be based on the context should be based on bytes, but I don't think that's useful. Maybe it is.
May I? I think that the context is used in patches because we are used to a human supervising the patching process and recognizing if something makes sense or not. In other words, we accept partial matches. So we take a patch and we apply to something which is not exactly the original file yielding the modified file. No, we apply to an origin which is different from the first A. We apply the patch to C, and then we get D as a result. So this we accept. With a binary file, we probably don't want to accept it. It's too risky.
Right. So I'm not sure to what extent that makes sense. Yeah. I mean, to support that. Yeah.
With poke, you have a degree of security because poke forces you not to break the format. So that is good. At least there are some stupid things that you cannot do, but it will not prevent you from doing semantically stupid things.
It depends. It depends. But yeah, I mean, this really should be useful for other tools as well.
I guess. Okay. I think Matthias should. Maybe Matthias has some ideas because he has a tool already, FQ. I think he's sleeping.
Probably. Okay, so so then I thought that to discuss about these kind of things, which are not poke specific or tool specific, I was considering creating a mailing list in binarytools.net. So, if people interested in this or interested or working on other tools, so we could have a common ground there, some sort of neutral ground where we could discuss about things like this. I will propose this after the summit. Yeah, okay, then I want to show you the implementation of STIF. You will see that it is not big. It is written in poke. And the implementation that I have now, it's basically coupled with the poke application, but I want to decouple the STIF functionality into a pickle that can be used by other programs as well, other poke programs. So let me show you. So this is pkdiff.pk in the poke source in the source directory of the poke application, the program. And like other poke commands, well, I have a couple of global variables here, which are the default values for that the command uses for the group by and the values arguments. Then here there is the addition in the poke help system of this particular command. So this is the help that you see when you do help Steve. You see, here it is. And then the first interesting part of the implementation is that I have a type, which is a diff thunk, which actually represents the thunk that is being made, right? And then it supports two kind of thunk lines, which is addition and removal. And then internally in the diff thunk, we have another type, which is a diff thunk line, which this represents every line. So plus bytes name value or minus bytes name value in the thunks. So here you have you have the kind, not how I am using a data constraint here just out of habit. Then the data name and value. So this represents one line in the thunk. Then this struct, it has, this Boolean, which is whether to emit values or not. The group by default is 1 byte. Then two variables A and B. Then the offset. So basically, this has the offsets of A and B, which are the ones which are in the header of the thunk, and the sizes of A and B. So A and B here are indexing those arrays. And then we have an array of lines, which are the lines that are being accumulated for the current thunk. So we have a method reset that it resets the offset and size, so it resets the header counters, the offset and the size of each thunk. And also it resets the lines array to an empty array of thunk lines. So this happens, this reset is called when we are done with the current thunk and we want to introduce a new one. This method, it adds a thunk line. Remember the thunk line here, which was it was either add or removal, the data, the name, and the value, which were strings. So this adds them. Basically, you pass what kind of line you want to append to the current thunk, addition or removal. Then you specify an array of bytes. Then you specify the name part and the value part, which are optional, as you can see. By default, they are empty. Here we are using this auxiliary function to get a string from an array of bytes, and this uses the group by value here, and this group by here used by this function inside this method is the group by field of the thunk struct here. Okay. So yeah, it's just you append a new line, and then it adds in the arrays of line. It inserts, it adds a new thunk line that we construct with the kind, with the data, which is we use this function to format the data string from the bytes, the name and the value. Easy. Now there is another method which is called print thunk, which is the one that gets invoked when we are done with the current thunk. We added lines, but we see that the next line will not be contiguous, right? So we need to introduce a new thunk. So we want to print the previous one, print it in the screen, in the terminal. So we call print thunk, which is a method that gets no argument and returns no value. So if the thunk is empty, which could happen, then it prints nothing. It prints no header because it doesn't make any sense to do so. then here it is formatting the strings for, I call here region to this offset plus size in the header of each thank. The one for the A, the one for the B, using format. Then I'm using, if you saw in the examples, it has colors, right? So this is with an underscore actually, but my terminal prints it that way. This is red, this is green, and so on. This is done, you know, from poke. We can print with the styling, right? And we do that with the term begin class and term end class calls. I introduced in poke several classes for styling. As you know, some of you know, poke installs CSS files, and this thank header. No, it's bold. It's not underline. So the thank header, div thank header, div minus, and div plus. So if you want to change the styling in your own machine, all you have to do is to change the CSS file or provide your own to poke. Anyway, so it prints the header of the thank, the region that we formatted here. They could be empty because look, if the size of A is 0, then it is the emptiest string, which is what happens in those thanks, which is only addition. Yes, if the case of the B, if it is 0, the size of B is 0, it is in the thanks which contains only deletions, removal lines, and then it is the emptiest string. And then it's time to print the lines with the information itself. For example, this was to print this header, and I want to print all the lines which belonging to this thank. And for that, we use the PK table pickle. We say we want the PK table is a pickle which is very written in poke itself, of course, which is useful to print tabulated data. So we say, okay, we want a table, which columns it depends. If we are including values, 3 columns, otherwise 2. Then for each line in the arrays of lines that we have accumulated, we add a row. We use the style. This specifies which styling to use in the row. In all the call, you know, in the row, it may be div plus or div minus, depending on the kind of the line. And then we add the name, and then we add the value. If first we add a plus or a minus, depending on the kind, and the data. This data is the formatted bytes, and then the name. And then if there is values, if we want to print values, we print the values, and then we print the table. And that's it. And then there are 2 methods left for the thank type. One is change, this one is used to express a change. To express a change which will result into the addition of a minus line and a plus line, which could be, is the screen share not working?
It works well for me.
Mohammed, it does not work for you? Okay, well, yeah, so this is a method that we say, you know, at this A offset and A size, there is a change from that, to this B offset and B size. Those are the bytes that are removed, and those are the bytes that are added. And then a name, if any, the names, if any, and the values, if applicable. And then this change method here says, okay, this is the conditional that checks whether we need to just add this information to the current thunk, which is this case, and then we update the header information for A and for B, or we have to print the thunk. This is calling to the print thunk method, and then reset the counters. And then in any case, it appends the lines, one rem and one adding, one for removal and one for adding, because this is a change, you know, as the method here says. And then another method is add rem, which is, this is either an addition, a pure addition, or a pure removal, right? Which what specifies if it is a removal or an addition here from this offset this size. And it's very similar to the other one, right? Depending on what we want, then we are removing, then we are adding a line to B or removing a line from A. So, and this is also the conditional that determines whether we are still in the current thunk or we have to change. It does the same thing, print thunk and reset, an append line. So this was the type, the diff thunk, the PK diff thunk type. Now let's see the command itself. The command itself is sdiff. As you can see, I mentioned it yesterday, but in POC, thanks to this alternative syntax we have for calling functions, we just implement commands defining functions, right? So sdiff is defined like this. So any A, any B, then this string, those prefixes are used to, as you saw in the output of the diff, basically the first symbolic for each name for each entry is A and then B here. You could change that if you wanted to by when you invoke sdiff, but actually have never tried to do that. Let me see. Oh, how it is called? Oh, prefix A and prefix B. Because those arguments are actually intended to be used in the recursive when you call. No, actually not, because it changed that. Yeah, okay, it works. Okay, so probably have to document them in the, because this can be useful too. Yeah.
I think this is useful for filtering too, because you know what's the prefix.
Yes, yes, yeah, okay, good. So I will document this here. Yeah. Okay, so then this is the optional group by, which defaults to this global variable. And the note, how we are using here, this is something I like about POC very much. Thanks to the lexical scoping, you know, things like this work and it's very comfortable. Like, for example, sdiff gets a thunk as an argument, so we just initialize it here, right? Which emit values P equals to values, and values is itself another argument that comes first, right, before it. And the same for group by. So those are, if you remember, those are the fields of the PK diff thunk type here. Yeah, emit values P and group by. Yeah, so those are initialized here. And then it returns void. Okay, inside sdiff itself proper, we have here format ename function, which is a utility function. This is not interesting. This is what basically this decides whether to put a dot before the name of the element, and this is basically what makes this to not insert a dot between the R and the open brace there. You see, for example. Anyway, this is not important. Then we have this horrible format value here. This will go away because we still have to add a dynamic formatter to POC, you know, for format values of type any, like this. So for the moment, we have to live with shit like this. So please ignore those lines there. they are trivial, but they are ugly and bulky. Then we have this function getElem bytes that you pass a function, a value of type any, and then this index, and then it maps an array of bytes corresponding to the element of this index of this value. So let me explain this a little bit. In POC, any value can be any value. Can be an integer, can be a string, can be an array or a struct. However, we have, in this case, we know, because this is warranted by this function somewhere else, that this V is actually a composite object value. It is either an array or a struct. So then we have those value attributes here, which work on values of type any, which gives you an offset. This one gives you an offset with the size of the element number IDX in this value. So this will be like the second element of the array or the second field of a struct, right? And this gives you the IO space where the value is mapped, the value that you map, and this gives you the offset of the element in this, the element number IDX of this value. So those are value attributes that work on any value of any type. Okay, this is a very ugly hack that again, this basically we use this to determine if this any value is composite. So it's an array of a struct. This will change too. But okay, so the main code is first we make sure that both values are mapped, because if they are not mapped, then it doesn't make sense to compare their bytes because they don't have bytes. And then this is the algorithm. It is very POC-ish, so because it uses, for example, this operator, which it's very POC specific. Well, it gets, you know, basically this says that. So this tries this line here. It goes to sdiff change here, and sdiff change it proceeds element by element of the element by element of the composite object and so on. You know. Okay, well, then if this results in a map in an out of map exception, then yes, then it tries to do the change of the struct itself as one element. This is related to the fact that there are because the diff format is byte oriented, fine, but so POC has to be, sdiff has to be a little bit smart here. Okay, we have an IO space open, it doesn't matter which one. But in POC, we can have structs and objects and values that are whose size is not a multiple of bytes, right? So for example, we can have this. Right? So the total size of this struct of foo is 1 byte, but the element foo in this case of this struct it is 5 bits long. So what happens if we say sdiff What happened? What happened is that POC did not basically went down, you know, to foo and b, but it gives us, you know, the difference of the enclosing struct that is a multiple of bytes. So it tries, you know, to be smart in this way, in this sense. Of course, if it is the outermost value that is not a multiple of bytes, then we get an exception. So for example, if we change this to be 4, then we get an invalid argument exception. It says the size of compared values is not a multiple of bytes, but it tries to do better. It's best, you know. So so yeah, that's why, you know, the code is the way it is. And that's it. I mean, the whole implementation is 366 lines, including this horror here, which should go away, and the documentation and everything. And this is it. Any questions, comments? About the mailing list, not only the mailing list, but my plan is actually to use binarytools.net, you know, as a sort of a common home, you know, for all the tools. For starters, you know, I will put links to all the different tools that have participated in this summit, and also we can have the mailing list. The IRC channel that we are using for the summit in Libera, it can stay too, and so on. Okay, so thanks for the thanks, and if there is nothing else, then we can call this a day.
Thank you, Jose, for the talk. Can you stop recording?
Yes.
Thanks.